All right, guys. We're going to be expanding this repertoire of functions that you should know. These are all shapes of functions you should know. Obviously, any even power function should look like a parabolic. Any odd power function should look like a parabola that had a rough night, so half of it fell out. Root functions look like basically take the parabola and turn it. Obviously, if they're even roots, you've got to kill the negative part. So this looks like a parabola has fallen over and the other part just completely fell away. I'm not allowed to be negative for the square root, but for the cube root, I'm allowed to be negative. So it looks like a cube root just turned over on its side. I mean, a cube turned over its side, sorry. So far, so good. I mean, these should be things you should already kind of know. So you have to know the shapes of these things, so when you have to go graph them, you only need a few points, not a bunch, because you should know what it should basically look like. Absolute value, of course, is the V. These are some that you might not be totally familiar with, but there's 1 over x. 1 over x squared kind of makes sense. 1 over x squared can't be negative, so it really just picks that up, makes it positive. How are we doing so far? This is also a very simple example of a type of hyperbola, but that comes much later. Here's something that this probably is new for everybody. It's called the greatest integer function. So, for example, if I had 1, the greatest integer that's less than that is 0, 0.9. The greatest integer that's less than that is 0. That's why the output is 0. So that's explained in the write-up. And this actually is very useful for real life. This is something like if you're charged for calling a phone number, you call the psychic hotline. You want to know what's going to be in the next test. And they charge you $4 for the first minute, and then $1 extra for every minute or part thereof. So it's $4 for 1 minute, $5 for 1 minute, 1 second, up to 1 minute, 59 seconds, and then $6 and then $7. So it's steps. It's not continuous. Does that make sense? So this actually does make physical sense for things like that, where you have, it steps up in amounts. Okay. But these are definitely, these here should be functions you have seen before and you know the shape of them. I wanted to let you guys try out a couple problems. Let's see. Based on what we're going to do next. Here we go. Perfect. Wow. Okay. So look at number 6. This is on page 169, if you have your book. I love this question because it's a very simple question that if you've never seen it before, it really freaks you out. It says, what is g of -2? And there's the graph there. So for this one, I don't even know what the hell g of x is. They don't tell me what it is. But the funny thing is, they've done the work already. It's easier. Does anybody know what g of -2 might be? Yeah, why? Because that -2, that's where it is. So if that's new to you, I want to know who your 110 teacher was. But beyond that, it's just as simple as where would you put the point? You would plug an x in and you would put the point where the y is. So somebody already did that. They already did the work. So g of -2 must be 4 because that's where they put the point. So what's g of 0? 7. You just go up to where at 0, the output is 7, so forth. Let that be simple. What about the domain and range? Domain, what do you look at? X values. So little dude walking. What's the first time he sees the graph? -2. So the domain would be -2 up to, looks like 5, 6, 7, 8. Sweet? They're a little evil because they didn't put open or closed circle, but you have to assume it's closed then. You have to assume it's there. You have to be more specific if it's not there. You kind of with me? So they're not maybe intentionally being evil this time. Say again? Yeah, bracket. I would put a bracket. I would include it like it's a closed circle. What about the range?
3 and 7.
Yeah, now I look at the y. The lowest output is 2. Up to 7, yeah. I like it. Cool. The value of x for which g of x is 4. We already know one of them. It was negative 2. Where else is the output 4? When x is 2. So you just got to do this thing. Here's 4. Here's the outputs of 4. There's one of them, and there's another one. 7. I like it. Do you guys see how to read the parts of a graph? I mean, you've done this kind of thing before, but very often you don't do exactly a lot of these little details in 110. So I don't know if I've called it this yet, but basically 176 is graphing hell. Right? It gets you ready for calculus. Even if you don't need to take calculus, you still need to pass this course, but it basically just you analyze graphs in every possible way you can imagine, and then some. And then when you get to calculus, that won't be the part that freaks you out. And even the calculus is not that big of a step away from algebra. So at that point, you should be really confident with what you're doing. Find the values for which g of x is greater than 4. So it's greater than 4 from what values? From negative 2, I put a parenthesis there because it equals 4 there, right? So from negative 2 up to the 2, again, another parenthesis, right? Anywhere else?
7.
Yeah, parenthesis 7, bracket 8. I like it because it stops there at 8. Sweet. How are we doing there? Is that, I see some. So that last one, part D, where is it greater than 4?
Right.
So right up here? So yeah, so it's greater than 4 in there. So it's greater than 4 between negative 2 and 2. And then it's greater than 4 again from here, 7 to 8. I can do a bracket. Yeah.
So you would be able to include those in one, or do you have to separate?
You have to separate them because there's no way to do it without somehow including the other things. You have to skip. So that's what I always look at the U like skip. From here to here, skip to here, skip. I always look at U as skipping.
You would have had a bracket negative 2, right? Bracket negative 2.
Not for the last one. Because that negative 2, it is 4. It's not greater than 4. So I can't include negative 2 in my answers. Cool. All right. Then they'll ask you stuff like, let's see if we can get this up here. Probably not, Jeff. Oh, here. Perfect. Like number 20, for example. Where's it increasing, decreasing? So where's it increasing? Let's do that first because it only increases in one interval.
0 to 1.
Yeah, it's not negative. It starts increasing at x equal to 0 and then stops increasing at 1. So from 0 to 1, it's increasing. I don't include those because those are turning points. This is actually a little bit more evil. This is not a turning. This is like a what they call a cusp. And in calculus, that's a problem. Calculus is not like that sudden. They're like smooth things. So 0 to 1 is where it's increasing. Where is it decreasing?
Negative 2.
Negative 2 to 0. And then 1 to 3. And normally for the endpoints, I put them in parentheses also because what's happening after that, I don't know. It doesn't exist after that. But on the endpoints, you actually could do either way. Okay. Cool. Oh, don't watch that. You'll get sick. Okay. Yeah. All right, good. So we already talked about increasing, decreasing, local max, local min. When they just give you the graph and they ask you for the max and min, it should be the whole number. Don't overthink it. They got to make it kind of nice if they have the graph made for you. So all I really want to do today, new, and that was all just kind of firming up and finishing out those first 3 sections, is section 2.4 and a little preview into 2.5. 2.4 is what I was saying earlier about we're going to see that idea of the rate of change function. It was that f of a plus h. It's f of a over h. It's not exactly that, but it certainly is related to that, because all that really is the slope. So section 2.4 is about average rates of change. Oh, thank you. So let me give you something that kind of builds on our own experience. If this represents me in a car, I'll show you here in a minute. So I kind of accelerate. From 1. Let's see what I want. Maybe I can sort of like, yeah, cool. Let's see. Then I go from here. I go to here. Okay. Going pretty damn slow. And this is position. And this is time. This is probably traveling down the 8 in the bad direction at a certain time of day. Hopefully it doesn't take 4 hours, but let's just go with this. Imagine if the 8 was further, and the traffic jam lasted the whole way down. Between 1 and 4 hours, how far did I go? So at 1, how far have I gone?
10 miles.
So after 1 hour, I've gone 10 miles. All right, that's about the speed I go sometimes. And then after 4, the next 3 hours between T1 and T4, how far have I gone then? 30. Right. I already went 10 miles. If I end up 40 miles, I've gone 30 miles. Everybody with me? How we doing? So how fast was it going on average from 1 hour to 4 hours? Yeah, because I went 30 miles. In how many hours? 3 hours. So I was going 10 miles an hour. Which actually sometimes you're like, that's good. And when that's good, you know everything's pretty bad. Or normal is the other word for that. Is everybody with me on this? I mean, we've done that kind of problem before. That's what I'm a math geek, so that's what I'm thinking about to pass my time, so I don't get a lot of road rage. Let's see, what's my average speed right now? But when I look at it, what did I really just do? What does this really represent graphically? Slope. Right? It's the slope between this point and this point. We did 40 minus 10, 30. The rise divided by 4 minus 1, 3. The run. We did the slope. We're telling history. So that's the average rate of change. That's on average how fast was it going? How was my position changing over time on average? It doesn't take into account how fast I was going, how slow. It kind of averages that out, makes it nice and straight, nice and smooth. So let me give you another specific problem, because there's not much more to this than that, to tell you honestly. In fact, to give you the formula, it's a little tiny bit different. Now, allow this to be old. This is old news. This is slope. But we're kind of putting it in a slightly different context. And the formula doesn't look immediately familiar, but it really is just y2 minus y1 over x2 minus x1. So let's see if they give us, here's something that's a little more interesting. If they give you a function, let's do one like, there you go, h of t. Find the average rate of change for, from t equal to 1, I'm sorry, negative 1 to 4. You could do this several different ways.
Plugging the numbers.
Yeah, one thing you have to do, no matter which way you're going to do it, you've got to figure out what the the outputs are. I know what the inputs are. I've got to know what the outputs are. So f of 4 equals,
1 squared. Minus 1 squared.
well, yeah, f of 4 and f of negative 1. So f of 4 would be negative 1, yeah?
20.
Sorry. Oh, yeah, I'm looking at a specific number, yes, so negative 1. So f of 4 is 24,
Yes.
right? 16 plus 8. F of negative 1 is 1 minus 2.
Minus 1.
Cool? You all right? All right. And now you just realize these are your points. There's your y's and there's your x's. So now just get the slope. And that is really following that idea, that definition here, but it's just the slope. So once I do this, I see my points, x, y, x, y. So now I just do the slope. It'll be y2 minus y1 over x2 minus x1. So always go in the same direction. You go this, you better go this. How we doing? I like that. Oh, yeah, some of you have very concerned looks, but they want to say how you're doing, like, fine. Yeah. Oh, yeah, H, thank you. Yeah, I get stuck with the F. So these should be H's, the H. All right, and then you just got to do that. It's no big deal here. We got 25 divided by 5 equals 5. So for this function, the average rate of change from negative 1 to 4 is 5. On average, it changed by 5
Like 5
per
over
step.
1? Like
So this is like, you can think of this is your answer, but you can think of that 5 per step. So it'll be 5 up for 1 over on average. So it could have went 10 up for 1 over, and then it would have went maybe 1 up for 1 over. You know, on average, it would come out to 5 increase. How we doing? So that could mean that this is something going up. You know, it's a balloon going up. If this comes out to be negative, that obviously means that it's going down, or you're going backwards. Your car, your velocity is negative, means you're going backwards. Is that cool? Okay. So here, you guys try this one. So, can you guys see that? The purple pen seems to have a really strong survival instinct up here. Does not want to go. see the first one real quick. G of 0 is 2. G of 5 is 1/3, right? 2 over 6, 1/3. So now you just have to find the slope. So you could do 1/3 minus 2 over 5 minus 0. And then you just got to finish that out. 1/3 minus 2 is 1/3 minus 2 is 1/3 minus 6/3. Negative 5/3. Divided by 5. Okay, or negative 1/3. Because the 5's just cancel. 5/3 divided by 5 is 1/3. Right, so the over 3 doesn't really change that idea. So that means this function from 0 to 5, overall it was decreasing on average. It might have had a little uptick, but the downtick definitely overpowered it. It came out negative on average. So it's on average it's decreasing between the two. All right. What about part B? It's the same idea, right? Sort of. But now I've got 0 to 5. G of 0 is still 2. I'm sorry, not 5. H. G of H is 2 over H plus 1. So now I just find the slope, like always, and do y2 minus y1 over x2 minus x1, so just h on the bottom. And now have some faith. This will always get to the point where h will cancel, believe it or not. What do I have to do up here? LCD, so 2 over h plus 1 minus, this needs h plus 1, right? So you get minus twice h minus 2. All over h. Is that all right? I know it's a little crooked. Just give me a break. I made it a little bigger there. So what happens on the top here? Do the 2's go away? So you get negative 2h over h plus 1 over h.
The H and H cancel.
Good, the h and h cancel. You get negative 2 over h plus 1. Let's check it. When h is 5, what did we get? Negative 1/3. So if I make h 5, I get negative 2 over 6, which is negative 1/3. So this is a more general application of what we did in part A. Yeah.
Can you explain the last step?
So we're cool up to here. LCD, the 2's go away. So I just have negative 2h over this and the whole thing over h. And then those h's cancel. And that's the part that people can't get over. If I have, stay with me now, if I had AH over H, what happens? H cancels. Couldn't A be whatever the hell I want it to be? Isn't that the idea? So couldn't I make A equal to negative 2 over H plus 1? So negative 2 over H plus 1 times H divided by H, the H's still cancel, right? If I have something times H divided by H, what happens to the H's? They cancel. We just get so hung up on this fraction inside of a fraction. Who cares? It's something times h divided by h. The h's go away. If you don't like that, you can just use the rule directly. Dividing by h is the same as multiplying by 1 over h. And the h's still go away. Cool. Is that right? Yeah. That's okay. That evil h is the one that goes away. And it's an evil h because in calculus you want the h to go to 0. And I can't just make it go to 0 here because that would be dividing by 0. Now could I make it go to 0?
Yeah.
Since I canceled that one out, sure I could let h be 0 now, right? So that's part of the whole calculus thing. You want the h to cancel so that you can plug a 0 in for it. You can't plug it in 0 until you get it to go away. Again, this is all a major preview. Okay. So how do you guys feel about that? I mean, the worst that they can make this is to throw variables in it, and it's still the same process. It's still slope. It's still whatever the outputs are subtracted over whatever the inputs were subtracted. You know, and then it should be some basic algebra to clean it up. You should not be really majorly freaking out on this. Freaking out a little bit's okay. I want to show you one more example that's got to do with a different format here, possibly. Let's say I'm climbing a mountain. Let's see, what do I want to call this? Okay, just won't use variables. So I climb a certain height, and then I take the temperature, and then I climb some more, and I take the temperature, and of course, what should be happening?
Higher you go, lower.
Exactly, right? So if any of you guys climb any decent distance, you know that all too well. Right? So let's say I climb, let's say 20 meters. This is in meters. And I find a temperature of 54 degrees. And then I climb, let's say, up to 180 meters. And now the temperature is 49 degrees. Now I like to hike, but I don't really go up very high necessarily, even though I wouldn't mind it. So I have no idea how close this is to reality. So just go with me for a second. It's still the same idea, but you got to be careful in this problem with the units. Units matter here. So if I ask you the average change in temperature as you move between these 2 points, how would you set that up? Do it again. What would you do?
Subtract the 20 from the 1.
This is in Fahrenheit. Yeah, what goes on the top?
180 minus 20. Oh, no.
Yeah, outputs, right? Your Y's, 49 minus 54. Or the other way around, as long as you do them both the same way. So 49 minus 54 over
180 minus 20.
180 minus 20. Yeah, negative 5 over 160, which is negative 1 over 32. What's your units, though?
Fahrenheit.
Fahrenheit, Celsius.
I like it. No Kelvin.
No, no Kelvin.
Fahrenheit degrees per
Meter.
meter. I like it. You can just say degrees for negatives. So be careful with a lot of these problems. For the ones that are just functions, and they'll tell you a damn thing about what it is physically. You just need to give me a number. But if it's a setup like this where it has physical meaning, you better give me the units at the end. And all it is the ratio of whatever units these were. Not a big deal. Yeah.
Where the negative sign goes to?
The negative should kind of flush out by itself. And it should match with physically, now not every situation will you know, but as I'm climbing a mountain, we already knew that it should go down. The temperature should decrease as it's going up. And that's exactly what it says. It's decreasing as I go up. 1 degree for every 32 meters that I go up. So that number actually exists. There's probably a kind of a standard that changes a little bit based on how high you already are. And what the,
Degrees for every 1,000.
all right, there you go. There's my climber. I got to convert that to meters to see how close I am to right. So 1 degree for every 100. So 100 feet, right? 10 for every 1,000.
10 degrees for every 1,000.
All right. I got you. Let's see if it'll come out. I got to store that in there now. I got my one more known conversion. All right. Is there any questions on that? That section should be relatively nice. Okay. So a little preview. Here's where things get a little more interesting. So a little preview of what we'll do next time. not transformations, the dark side of the moon. One person. I like it too, so that's stupid. Transformations means taking a function and just moving it. So I can take a parabola and move it over here and move it down there. Move its vertex essentially, right? So the whole thing's got to go with it. Take a circle. The center of every circle is not 0, 0. So there should be some way to represent moving that circle around. And what would that do to the equation? Or the opposite. Here's the equation. What would that do to the graph? So let's start off kind of nice here. If I have what does that by itself look like? This is what I call the base function. Sort of sounds like we're still on the climbing a mountain analogy.
Looks like the tilted half gravel.
Yeah, exactly. So it's got to look like the lowest number you can put in there and get a real output would be 0. 1 goes to 1, 4 goes to 2. So it's going to look like a parabola that's fallen over. Okay. Make your points big and you're fine. So the idea of transformations, and this is actually decently important because later in mathematics you start, we're going to do transformations like moving it over, moving it up or down. We can even flip them. In later math you learn how to rotate it a little bit. That's a little more complicated. So we're not going to do that here. So if I do this to it, think about what that means. That means, now here, what's the smallest x I can put in there? 0. Here, I cannot even put 0 in there, because the first thing I do to my input is make it go down by 2. So my inputs all have to be bigger than they normally would. So the whole graph should actually move this way. All my domain elements have to be bigger than they normally would. So the funky thing about this, and this is a semi-evil little thing, but basically, if the number is in with the variable, it does the opposite of what it looks like. That's -2. It's actually going to make it go to the right 2. So it would take, my base function is this. So it would move that point over 1, 2, that point over 1, 2, and that point over 2. And there's my shifted function. So this would be a shift right 2. So if I wanted to shift back 2, left 2, what would I have to put in there?
Plus.
And that's, so normally a square root can't be on the negative side, but if I put a +2 in there, all the inputs can now be smaller than they were before. So it would end up making my go back on the x-axis. So the whole picture just moves back. It's kind of nifty. So now you can take any function. It doesn't have to be square root. I could have put x squared and then x minus 2 squared. It would have been the parabola, and then the parabola moved over 2. It would have been the same idea. Doesn't matter what the function is. It's going to do the same thing. This becomes huge when we get into stuff like trigonometry. So if I have any musicians out there, or possibly even better sound engineers or people that work, anybody in here do that? Lights and sound maybe for a little bit? So if you're mixing sounds and so forth, you would be very curious about the sound waves that look like sine waves. And if you're mixing them, you want to be careful about, am I hitting the 2 waves at the same point so that they constructively add and stuff like that? So most of you guys are like, I don't know what that was talking about. But I want to be able to move the functions around until I get them to maybe line up so that they'll constructively add so they get a louder sound possibly. Or I want them to cancel out. Make some white noise and cancel out some other noise. You know, so it depends on what, so I might want to move it around a little bit. This is exactly how you achieve that, equation-wise. Okay. If I were to put something out like that. Now what does that do? What does that by itself do right there? So that would be to the right 1. I love it. Up 4. Not down. And let me show you real quick. And that's where it's going to get through. So if I have this, this is definitely to the right 1 because that -1 is with the x. If I move that 4 here with the y, now I can actually see it a little better. So that would be up 1 and it would be up 4, right? Up 4. You with me? But since it's over here, it's actually a little easier to look at, to tell you honestly. All it does is, whatever the hell that is, all the outputs are now 4 bigger than they used to be. So of course the whole thing just moves up. So I would do like this. My base function, 0, 0, 1, 1, 4, 2. So for any function I do, I try to have 3 points that are like my anchor points. And then I just move those and then just draw the picture on top of it. So now here's my base function. I'll want to move it right 1, up. Might have to do 4. Oh well, these things happen. So I want to move right 1, up 4. Right 1, up 4. Right 1, up 4. Bam. Right? I didn't have to do anything, any plugging in of stuff into this thing directly. I could just use this that's quick, and then move it that's quick. How do I check myself? Check this. So, like right here, what point is this? 2, 1, 2, 3, 4, 5, I think. If I plug a 2 in, do I get 5? Yes. 2 minus 1 is 1, square root of 1 is 1, plus 4 is 5. Sweet, that's how you check yourself. Take a point from where you ended up, make sure it works in that equation. If it does, you're good. At least for that point. All right. Let's see. So that's my little, obviously there's going to be a lot more. We're going to do shrinking and stretching and flipping and all this other kind of transformations. Yeah. Think about what this means to the numbers I put in. Normally to get 0, I would put 0 in. Now how do I get 0 in here? What number would you put in to get 0? 1. Isn't it 1 bigger than it used to be? So the whole thing would shift up 1. Just because of the reality, all my inputs have to be 1 bigger than they used to be just to overcome the -1 that's happening to them. Does that make sense? Because that, to me, as a student, I remember I was a little bit irked because I like things to be, I should be able to see what's going on, but it's like, that says minus, dude. What the hell? But it's that overcoming the minus. So they all have to be bigger. That's why the graph actually goes the opposite way. Maybe. Okay.
No longer finger crossed.
I know, man. I need... All right. Okay, so what's going to happen next time is this. You're very interested in this. Quiz. Chapter 1. And actually... yeah, and some basic function stuff too. So like chapter 1, 2.1 and 2.2. Wednesday. You guys realize what's happening a week after that?
We have a test.
Shit. Right, so on Wednesday I'll also have the practice test. I'll give you a practice test. And the following Monday will be review day. There won't be anything new. We'll just look at the practice test. I'll have the answer key. We'll talk about whatever the hell you want to talk about. Right, I'll have the quizzes graded Monday, so I'll give those back to you. You can make corrections. So don't forget to test the following Wednesday. 1 and 2. Hopefully we finish up chapter 2 on Wednesday. If we don't, I'll just change what's going to be on the test.
No, I'm sleeping.
Quiz is normally like 5. They're really short to the point, nuts and bolts. You get the basics. Test, 20 total. I always hate it when somebody says, how many questions on the test? 5, and they all actually have A through J. You're like, that's not 5 problems. So I normally do 20 to 25 problems, counting all the A through J stuff. Okay. All right, that's it. Get out a little early again. Don't get too used to it. What's that?